AB Calculus BC, Unit 7, Day 9, Office Hours, Rate Model, Free Response Problems. So this one's all the way back from 1996. You can use your graphing calculator on it. That would be the year I took the AB Calculus AB exam. Rate models are pretty much AB problems. The rate out of consumption of coal in the United States. That's the rate of consumption. S is measured in billions of gallons per year. So this is a rate. T is measured in years from the beginning from 1980. The consumption rate doubles every 5 years, and the consumption rate at the beginning of 1980 was 6 billion gallons per year. Find C and K. C and K. So this is pretty much exponential growth. C is some initial condition. So since 1980, doubles every 5 years. So we could find the K value by using the fact that it doubles every 5 years, doubling time. Divide by C. Take the natural log of both sides. Divide by 5. So K equals natural log of 2 over 5. And so that's the K. It says find C and K. I think C would be just times 0. You would get C e to the K times 0, and that would be, this would be in 1980. This would be the rate 1980, which they said doubles every 5 years. The consumption rate at the beginning of 1980 was 6 billion. So C equals 6 billion. It's 9 billion gallons of cola per year. Probably should put units on all your answers. Okay. So, yeah. You could, yeah. All right. So that's A. B says find the average rate of consumption. So we're looking for S average over the 10-year period beginning January 1st, 1983, indicate units of measure. So I think we need to use mean value theorem. Even though S is a rate, we don't have the original function that it's the rate of. So we don't want to use the regular mean value theorem for a function. So we want to integrate the function from 3 to 13. 10-year period started in 1983, and T is time since 1980. So 1983 would be 3. And then you're going to divide by the base of the rectangle, smooth that curve to get the average height. And I guess we should use our newfound function. So you guys show the setup. And then we can put this in our calculator. And I mean, we can use a graphing calculator, so we might as well just use a graphing calculator. 0.1, math 9, 6, e to the natural log of 2 close x divided by 5 close comma x comma 3 comma 13. You get 19.680 billion gallons of cola per year. This is an average per year for those years. So C, use a trapezoidal rule with 4 equal subdivisions to estimate 5 to 7 of STDT. You can use trapezoids to estimate it. I mean, I don't know if I really want to draw a picture because these numbers are going to probably be kind of, maybe a table might work nice. And plug them into S. So 5 to 7, 4 equal subdivisions. So it'd be 6, that'd be 5.5 and 6.5. And I mean, you could plug this function in. What was it? 6e to the natural log of 2 over 5t. 6e natural log of 2 x divided by 5. We get to go to a table and put these values in: 5, 5.5, 6, 6.5, 7. So I'll just put those down. So this is 12. Might want to highlight them to get more than 3 decimal. Actually, 12.861281, 13.784380, 14.773732, 15.834094. So the trapezoids, you should show your setup. So we want to do average of, these are going to be the bases, and then the height of each trapezoid is going to be 0.5. So average of the bases is going to be S5 plus S5.5 divided by 2 times the height, which is 1/2. And then S5.5 plus S6 over 2 times the height, 1/2, plus S6 plus S6.5 over 2 times the height, plus S6.5 plus S7 over 2 times the height. So that's our setup. And then I guess we could try and use these values in here to calculate this. This isn't going to be super easy. So we do, we just do divided by 4 each time. So we could say 12 plus 12.861281 divided by 4 plus 12.861281 plus 13.784380 divided by 4 plus parentheses 13.784380 plus 14.773732 divided by 4 plus parentheses 14.773732 plus 15.834014 divided by 4. And there we go. 5 to 7 S of t dt is approximately 27.668. And so we're integrating the rate. So that's going to give us gallons of billion gallons of cola consumed from 1985 to 1987. That's the meaning of it, which they often ask you for those kind of things. That's part D. So part D says, what is that? These are great. Explaining to me is 5 to 7 of STDT is the total consumption of cola in billions of gallons of cola from 1985 to 1987. So we don't actually need to use the estimate. They ask us to directly interpret that. So there you go. We can use graphing calculator on this one also. Water is pumped to an underground tank at a constant rate of, oh, actually, this is no graphing calculator. So water is pumped into an underground tank at a rate of 8 gallons per minute. So I'd call that the entering rate. Water leaks out of the tank. This from 0 to 120. So this is the leaving rate. T equals 0 to 30 gallons of water. That's your initial condition. So amount at 0 equals 30. How many gallons of water leak out of the tank? So I might be tempted to just kind of try and write my overall rate model. It's going to be the initial amount, which is 30, plus 0 to t of the entering rate, which is 8, minus 0 to t of the leaving rate, which is square root of t plus 1. So that's my rate model, which I might use at some point. A says how many gallons of water leaked out from 0 to 3, just out. So that's just going to be the out part, 0 to 3 of the square root of t plus 1 dt. Now we don't have a graphing calculator, so we've got to integrate ourselves. So this is 1/2 power. So it's going to be t plus 1 to the 3 halves. It does have an interim function, but the derivative inside is just 1, so really unnecessary to use substitution. I'm going to plug 3 in. Square root of 4 is 2 minus 2/3. If you plug 0 in, square root of 1 is 1. So you get 4/3 minus 2/3 is 2/3. Actually, I made a mistake. Square root of 4 is 2. Cubed is 8. So that's 16. It's 14/3. 14/3. The units are gallons of water. And you can make this more descriptive, leaked out of the tank from time t equals 0 to t equals 3 minutes. I'd just be carefully putting units and stuff. Okay. All right. So B says how many gallons of water are in the tank? Well, that's going to use your rate model at time 3. So you're going to put 3, 30 plus 0 to 3 of 8 dt minus 0 to 3 of the square root of t plus 1 dt. Now we did just find this number, so I think it would be okay to not find it again. This is going to be 8t from 0 to 30. Which is going to be 24 minus 0 minus 14/3. So least common denominator would be 3. So this is going to be 90 plus 72. That's 162 minus 14. 58, 148 over 3. or it's almost 50, it'd be what, 49 1/3 gallons of water in the tank at time t equals 3 minutes. All right, good descriptive answer. Okay. Point breakdown, by the way, on this problem is 3, 1, 2, 3. First problem, you got 1 point for setting up the integral. You got, or 2 points maybe, and then 1 point for the answer. Part B, you just got one answer, 1 point total. Seems like you should get more for that. C says, write expression for AT, the total number of gallons of water in the tank at time t equals t. Well, we already did that. AT equals 30 plus the integral 0 to t of 8 dt minus 0 to t of the square root of t plus 1 dt. The only thing I could think is that maybe we should actually go ahead and integrate these. I think this would be good enough, but we could maybe take it further and say, okay, well, this is going to be 8t, 0 to t, minus this is going to be t plus 1 to the 3 halves divided by the new exponent, 2/3, 0 to t. And so then we're going to get 30 plus 8t minus 2/3 t plus 1 to the 3 halves minus, but becomes positive 2/3. So, this is a little more of an expression without integrals. But really, I think this first one was good enough. 1 point for the entering rate, 1 point for the exiting rate. Okay, D says, at what time t 0 to 120 is the amount of water in the tank maximum? Justify your answer. So we're looking for the max. This is extreme value theorem, very typical question on rate model problems. We're really good at extreme value theorem. We have this rate model. The endpoints are 0 to 120, so that's already figured out for us. We need to find critical points by taking the derivative of the thing that we're trying to maximize, which is going to just give us the entering rate minus the leaving rate, right? Fundamental theorem of calculus part 2, derivative 30 is 0. So it's going to be 8 minus the square root of t plus 1, and we're going to set it equal to 0 undefined. This is all work you should show, labeled, show it being set equal to 0 undefined. In fact, this was a point right here. That's a point. Now we should solve it. 8 equals t plus 1 squared, 64 equals t plus 1. T equals 63. That's another point. That's your critical point. And then we're going to make a table. Endpoints are 0 and critical point 63 and 120. So I guess we got to do this work here. Plug 0 in, you get 30. That one's easy. 63. I guess I'm going to go ahead and use this other version of it that I already wrote. So that's going to be 30 plus 8 times 63. What's 8 times 63? 24, carry the 2 to 48 is 50. So that's 504 minus 2/3. 64 squared 64 is 8 to the 3rd power. Oh my gosh. 8 times 64. 32, carry 3, 48 is 51, 512. So you can get 512 times 2 is maybe we should just leave that 512 times 2 over 3 plus oh, that's what the 2/3 should be. Plus 2/3. Okay, I think 3 goes into 512. 512 divided by 3, 1, 21, 7, or maybe not. 5 plus 1 is 6 plus 2. No, okay, it's not going to go. Okay, least common denominator would be 3. So, I don't know if I want to do that. 10, 24 divided by 3. So what is that? 341. So this is 341 and 1/3. And so let's see, this would be, and then with this, that's going to be 340 and 2/3 negative. And we have 534. So 534 minus 340. This is just a little tedious. It's going to be 194, but then you're going to subtract another 2/3. So this is going to be 193 and 1/3. 193 and 1/3. We got 30. Now we got to do 120. Even bigger numbers. 30 plus a 960 minus 2/3. 121 square root of 121 is 11. What's 11 cubed though? 11 times 11. 11 times 121. 1, 2, 1, 0, 1, 2, 1, 1, 3, 3, 1. 1331 plus 2/3. Okay. So we're going to give 2,662 divided by 3, 8, 8, 7, and a remainder of 1. Okay, so that's what we're subtracting there. If we add 2/3 to it, it's going to be negative 886 and 2/3. And then we have 990. So 990 minus 886 would be 401, 104. But then you can subtract another 2/3. So it's going to be 103 and 1/3. So this is your max. This is your min. This is a mess. I really should have done this probably cleaner, but whatever. So let's write this answer. The maximum amounts of water in the tank is 193 and 1/3 gallons at time t equals 63 minutes. Let's justify it by extreme value theorem. How does that work? By checking endpoints and critical points. Wow. Okay, so 3 points there. 1 point for just setting derivative equals 0. Then 1 point for your answer, and well, actually 1 point for critical point, and then 1 point for your work and your answer and your justification. Okay. Let's do another one. The number of gallons P of pollutant in a lake changes at a rate of, so they're giving you P prime, and this is P, where T is measured in days. There are 50 gallons of pollutant at the lake at time 0, so that's P0 equals 50. The lake is considered to be safe. This is a gravity diagram when it contains 40 gallons or less of pollutant. A. You know what? Let's just start by writing our rate model. I'm going to use PT instead of A equals P0 plus the integral of what's entering minus the integral of what is leaving. 0 to t, but so the initial amount's 50, and the entering rate, I would say, is the 1 minus 3e to the negative 0.2 square root of t, or that's just the overall combined rate. It doesn't seem to be a leaving rate, though. But anyways, that's just something that A says, is the amount of pollutant increasing at time t equals 9? So amount increasing, decreasing would be the derivative. Plug 9 into it. The square root of 9 is 3. So we could just calculate that on our calculator. I mean, we might need to do a bunch of calculations with this rate. So I think I'm going to go and just type it in. 1 minus 3e to negative 0.2 square root of x. Then we can go to the table and type 9 in. And that should be the same thing as this. I mean, we could check it. Negative 0.646. But 1 minus 3e to negative 0.6. Yep, same thing. Okay. Okay. So, and this is gallons per day. Those are units. Now, because it's negative, it's decreasing. Is the amount increasing? No. The amount of pollutant is decreasing at time t equals 9. Is t in days? Days since p prime 9 equals negative 0.464 is negative. So something like that. Explain it. All right, point breakdown here is 1332. So that was 1 point. That's a typical question on a rate model, though. They'll ask you about increasing, decreasing. You got to just find them out. For what value of t will the number of gallons of pollutant be at its minimum? So we're looking for a minimum. We're looking for an absolute min. So we should do extreme value theorem. It doesn't really give us endpoints. It says for what value of t will the number of gallons of pollutant be? So I guess we're gonna have to rely on like first derivative test, which is a little annoying. We definitely need to find critical points. So we need to take p prime 1 minus 3e to the negative 0.2 square root of t and set it equal to 0 undefined. And I don't think it's going to be undefined. So, and we could solve this by hand. Add this to the other side, divide by 3 is going to be 1/3. This is 1 over e to the 0.2t square root. We could flip both sides. Could raise both sides, or we could take the natural log of both sides. divide both sides by 0.2. And then square both sides. So this is a critical point, which is probably where it's going to happen since we don't have endpoints. We could calculate what this value is. Natural log of 3 divided by 0.2 equals squared 30.173724. So I guess we could do like a line check for P prime just to kind of see what's going on. So we have this value, which is about 30. So we could test a point t equals 0, that'd be nice, into this. That's going to be either, that's going to be negative, positive. So it's decreasing, it's increasing. This is a relative min by the first derivative test, and it will be an absolute min because the graph just goes down forever. So we need to explain that. We could say you got to first justify that you have a relative min, and then continue to show why it's an absolute min. So P has a relative minimum at t equals natural log of 3 over 0.2 squared days by the first derivative test for relative extrema. You got to explain how that works. Since P prime of t is negative on t equals 0 to natural log of 3 0.2 squared, and P prime t is positive on t greater than natural log of 3 over 0.2 squared. Okay, so that proves the relative min. And since P prime is, or since P is decreasing everywhere everywhere t is less than 0 with natural log of 3 0.2 squared, and P is increasing everywhere t is greater than natural log of 3 over 0.2 t squared. It must be an absolute minimum. I didn't find the absolute minimum value. Did they say to find the value? What happens? Is for what value t? So that's enough. We don't need to find the absolute minimum. You could by plugging it back into p, which we don't. Yeah, we could do it, but so that's kind of annoying. Is C is like safe when the number of gallons of pollutant is at its minimum. So I guess we got to find the actual absolute minimum. Plug natural log of 3 over 0.2 squared into our rate model. 50 plus the integral of natural log of 3 over 0.2 squared of 1 minus 3e to the negative 0.2 square root t dt. So let's calculate the amount there. So I already have it. I put that equation into my Y menu, so I'm going to take advantage of that. So I don't have to retype it. It's going to be 50 plus math 9 bars, y bars, function y1, comma x, comma 0, comma parentheses, natural log of 3, close, divided by 0.2, close, squared. And then we'll calculate it. See what we get. Show your setups and all this stuff. So we get 35.104338. Okay, so that's the amount of pollutant at that minimum. And they said that the lake is going to save when it contains 40 gallons or less. Well, this is less than 40 gallons. So we could say the minimum amount of pollutant is 35.104 gallons at time t equals natural log of 3 over 0.2 squared days. And since this is below 40 gallons, the lake is safe. Okay, so I think 1 point for having this in your work, and maybe 1 point for the answer, and 1 point for the interpretation of the safe or not. Okay, D says investigator uses tangent line approximation to PT at time equals 0 as a model for the amount of pollutant intake. At what time t does this model predict that the lake becomes safe? Tangent line approximation. This is like Euler's method, but one step. This is all calc AB. Tangent line approximation to PT at t equals 0. So we need to write the equation of the tangent line, I think, right? P prime at 0 is 1 minus 3e to the negative 0.2 square root of 0. That's going to become 1. That's going to be negative 2. So that's your slope. We have the amount at time 0 that gave it to us is 50. So we have everything we need to write the equation of a tangent line. So it's going to be y minus 50 equals negative 2 times time minus 0. And we put a p for pollutant. So PT is approximately negative 2t plus 50. That's your tangent line approximation. Identifying the slope was worth a point. Okay. So we want to know when will this predict it being safe. So we're going to set it equal to 40. That's when it's going to be safe or not, and solve it. Negative 2t equals negative 10. T equals positive 5 days. So this model predicts that the lake becomes safe at time t equals 5 days. All right, last one. Point breakdown here is 2, 3, 2, 2. The rate at which people enter an odd term of a constant is modeled by the function r, 0 to 2. R is measured in people per hour. No one is in the odd term at t0, so the amount at 0 is 0. When the doors open, the doors close, and the concert begins at time t equals 2. So that's why it's 0 to 2. So A, how many people are in the auditorium when the concert begins? Well, let's write a rate model. AT equals A times 0 plus, I don't think we just have an entering rate. I don't think we have a leaving rate. No one's leaving yet. So this is a generic rate model. That's going to be 0. So for us, the amount times 0 is 0. So it's going to be 0 to t of, in our problem, we call RT dt. And you can just write that. I mean, you could write it more. Now, I think it might be handy to go ahead and type this into my graphing calculator like this. But it says, so part A, we want the amount at time 2. Well, that's going to be 0 to 2 of RT dt. And that's your setup. That's good enough. But I think it might be good to just type this in. So it's going to be 1380 x squared minus 675 x to the third. Quit. So we do math 9, vars y, vars function y1, comma x, comma 0, comma 2. Ooh, it doesn't like that. What did I type in wrong? Looks fine to me. 13 years. Okay. Back to the home screen. Why? Why does that not work? Maybe I'll try just typing it directly in. 1380 x squared minus 675 x to the third, comma x, comma 0, comma 2. And then I forgot to put another comma. Now that worked. We got 980. Did I mistype it? My Y menu? Doesn't look like it. That's weird. Okay, well, whatever. Okay, 980. People are in the auditorium when the concert begins. That's our answer. Points, 1 point for your setup, 1 point for your answer. B, this is a graphing calculator problem. Okay, B says, find the time when the rate at which people enter the auditorium is maximum just for your answer. So we're looking for max rate. So we're not looking for max amount of people. We're looking for max rate. I think we have endpoints, right? This is when the rate exists. So we want to take the derivative of the rate, which would be 2760 t minus what's 3 times 65. 15 carry the 1, the 21 is 22, carry the 2 to 18 is, so that's going to be 2025 t squared. So the equal to 0 undefined. We have a calculator, but I don't know, I feel like we could probably pull this off. And we could factor a t out. So t equals 0, and t equals 2760 over 2025, which is ugly and messy and not reduced, but who cares? Should be fine. I mean, or we could use your graphing calculator to solve it, but I think that's all right. Let me see. What's 2760 divided by 2025? Same thing you get on your calculator. So on the calculator, what you could do is you could turn this guy off, type this in 2760x minus 2025x squared, window 0 to 2, -1 to 1. Look for the x-intercept, second calc, 0. Looks like it's between 1 and 2. Guess 1.5. And you get it 1.362. So if you did it that way, you get 1.362963. But that's the same thing as 2760 over 2025. All right, so this is your critical point. And then we should do extreme value theorem. Make a table, T. We're going to plug it into the rate. Zero, 2760 over 2025. 2, plug 0 in here, you get 0. Now I think I typed this into, I'm going to get rid of that. I think I typed that in. Did I type it in correctly? That's the only question. I think I did. Let's go to table. Let's try and use the table. We can put 0 in there. Oh. I gotta turn it back on. It's really not liking that equation that I wrote. 1380 times parentheses. Oh, that's what I did wrong. I said x caret squared, but I should just say x squared. Okay. 0, 2760 divided by 2025 and 2. So these are our rates. I'm going to highlight them to get the more accurate. 854.527,297. And this one is exactly 49.8. So here's your max rate. Here's your min rate. Use extreme value theorem. So the maximum rate at which people enter the auditorium is 854.527 people per hour at time t equals 2760 over 2025 hours by extreme value theorem checking endpoints and critical points. All right. Let's see. So points on that. 1 point for this. 1 point for your critical points. 1 point for your answer and analysis and justification. C says the total wait time for all people in the auditorium is found by adding the time each person waits, starting at the time the person enters the auditorium and ending when the concert begins. The function W models the wait time for all people who enter the auditorium before time t. So we have a wait function equals wait time for all the people. the derivative of W is 2 minus T RT. It says find W2 minus W1, the total wait time for those who enter the auditorium after T equals 1. So I think we need to use fundamental theorem of calculus part 1. So if we integrate W prime, we get W. And if we know, and if we do it between two different times, time 1 and time 2, time 1, time 2, W2 minus W1. So we want to do this. We want to W2 minus W1 is going to be the interval 1 to 2 of 2 minus T RT dt. So we can enter that in our calculator. I finally got my RT correct. So this is going to be math 9, 2 minus x, bars y, bars function y1, comma x, comma 1, comma 2, and we get 387.500. So the total wait time for those who enter the auditorium after time t equals 1 hours is 387.500. Is it hours? 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 It's some kind of time. Seems like a lot of hours. That's it. All right, D. On average, how long does a person wait in the auditorium for the concert to begin? Considering all people who enter the auditorium after the doors open and using a model for total wait time from part C. So we want to find if you want the average wait time, then you need to find the total wait time and divide by the number of people. Use the total wait time from part C. And just the function, I guess, I'm assuming, the function. So we need to find the wait time, W2 minus W0, find the total wait time for everyone from 0 to 2. So that's going to be 0 to 2 of W prime T dt is going to be 0 to 2 of 2 minus T RT dt. So we need to calculate that. So nice thing is it's the same calculation as before. Just change the 1 to a 0, and we get 760 for the total wait time. And so average wait time, this is my strategy here, equals total wait time divided by number of people. And so we got 760 total number of people. Oh, we already found that on part A. It was 980. So that can be our answer. We could change it into a decimal if you want. 760 divided by 980. 0.77555102. So there it is. The average wait time for all people is 0.775 hours. Oh, that's kind of tricky. That's it.